Traditional water infrastructure suffers from a severe blind spot. It relies on passive, unmonitored physical assets. Underneath our cities, a high-pressure pipe can rupture and violently leak water into the surrounding soil for weeks, entirely unnoticed. Because legacy networks depend on infrequent, manual data collection, these undetected leaks result in massive volumes of non-revenue water loss before anyone knows there is a problem. Simply reinforcing physical infrastructure cannot solve this. The true bottleneck is the inability to detect system anomalies the exact moment they occur. Without continuous telematic visibility, managing utility networks is forced into a permanently reactive and highly costly maintenance cycle. This diagram illustrates the necessary shift in infrastructure. On the left, a traditional grid relies on isolated, infrequent pulses representing manual data collection. On the right, we transition to an active IoT telemetry network covered by a dense digital mesh. This continuous data pipeline moves physical edge metrics directly to enterprise asset management platforms. To understand how this continuous visibility is achieved, we must map the specific hierarchical telemetry topology engineered by iEngineering Australia. Success requires a reliable hardware-to-software architecture to make this data instantly actionable. The data foundation begins at the physical endpoint. To capture precise metrics, the system utilizes high-accuracy ultrasonic and electromagnetic water meters. This diagram highlights a critical engineering transition at the edge. The top screen displays a legacy 4 to 20 milliamp analog signal, susceptible to noise and degradation. The bottom screen shows the shift to purely digital communications, a discrete packet transmitting precise numerical metrics. Deploying digital communications allows these meters to capture high-frequency totalizer logs and vital system diagnostics. These digital diagnostics continuously scan for two primary anomalies: continuous flow, which indicates leakage, and reverse flow events. These edge devices operate in severe environments, necessitating IP68 or explosion-proof housings. They also incorporate built-in battery failsafes to ensure operation during grid power outages. The ultimate requirement for an edge node is to remain physically indestructible while generating precise digital data, regardless of external power conditions. Allowing thousands of individual edge meters to communicate directly to the cloud presents a strict logistical bottleneck. It rapidly drains local batteries and overwhelms wireless bandwidth. The first architectural solution is a move away from direct-to-cloud connections toward a hierarchical sub-metering topology. This diagram models the first layer of that hierarchy, the RMT, or Remote Management Terminal. Inside an industrial site, up to 40 individual water meters feed wired connections into a single localized aggregator. This aggregation operates within precise parameters, linking up to 40 meters via RS-485 or Modbus within a strict 150-meter radius. Local RMT aggregation completely removes the wireless transmission burden from the individual edge meters, solving the power constraint at the endpoint. To connect multiple isolated RMT clusters across a sprawling industrial precinct, the architecture moves up the network hierarchy. As we zoom out on this diagram, we see the regional wireless hub, the GRM or GPRS transmission gateway. Here, aggregated data from individual clusters wirelessly beams to a single central tower. At this layer, one GRM collects wireless telemetry from up to 32 separate RMTs within a 1-kilometer radius. Scaling to full capacity, a single GRM orchestrates the packet flow for up to 247 individual edge meters simultaneously. This specific hierarchical architecture drastically optimizes cellular transmission costs while maximizing operational uptime for the entire multi-building site. With data consolidated at the regional physical gateway, the process shifts to the cloud backhaul. The external backhaul utilizes reliable transmission mediums, specifically 3G, 4G, GPRS, or narrowband IoT networks, to push the payload to central servers. Receiving raw, time-stamped data on a server is insufficient for actual utility operations. It must be translated to integrate with existing corporate software. This schematic illustrates the translation. Raw telemetry packets pass through specific software bridges, using protocols like REST, MQTT, and Modbus TCP, emerging as categorized, legible database entries. Telemetry data remains operationally stagnant when trapped in isolated hardware silos. Protocol bridges provide the necessary translation for enterprise systems to utilize these edge metrics. The first enterprise destination for this translated data is a SCADA system, establishing real-time global monitoring. Technicians utilize these SCADA interfaces to actively visualize water quality, system pressure, and multi-site status maps anywhere they have access. This diagram maps the second critical destination, Enterprise Asset Management, or CMMS platforms. Here, an anomaly like a reverse flow event from an edge meter bypasses manual SCADA observation and instantly generates an automated work order inside the CMMS. This is an entirely event-driven workflow. Predefined abnormal patterns bypass manual analysis and directly trigger actionable maintenance requests. Integrating edge hardware directly into a CMMS successfully transforms a physical infrastructure anomaly into an immediate, automated operational response. This end-to-end integration enables a highly efficient operational philosophy known as management by exception. Under legacy methods, crews conduct routine manual site visits. Now, technicians deploy strictly when the CMMS flags a specific, verified anomaly. This chart quantifies the financial impact. By eliminating unnecessary truck rolls and manual meter readings, exception management drastically lowers operational expenditure. Simultaneously, the early flagging of continuous flow patterns protects asset measurement integrity and sharply reduces non-revenue water loss. The true return on investment for an IoT water network is measured directly by the physical labor and wasted resources it eliminates. Successfully implementing this specific hierarchical architecture requires rigorous engineering tailored to strict environmental and regional constraints. Advanced systems providers like iEngineering Australia actively deploy and scale these integrated hardware to software pipelines across territories like Australia, Fiji, and India. Modern smart water management represents the fusion of civil plumbing, rigorous data architecture, and intelligent enterprise integration.